Hello everyone, welcome to the final video on a series on Laplace transforms. So we pretty much covered all the important topics on Laplace transforms with the exception with one very powerful topic, which is the convolution. Convolution, we need to define what a convolution is of two functions, and the definition involves an integral, so we're going to learn about the convolution integral. And we're also going to take a look at a very powerful theorem called the convolution theorem. In this discussion, when we're done with this, there's again the mathematical aspect of things. Basically, giving you the definition, show you how to find the convolution, and then showing you how the convolution theorem works. And that's where typically the math lesson finishes. But many of you are going into engineering, and many of you might take circuit analysis or do control theory. So you're going to find yourself working with the convolution theorem, but you'll go slightly beyond, you go farther beyond what we're going to talk about in a math class. So I will give you a little glimpse of some topics that when you go into those courses and hear about them, they will start to kind of make sense to you. At least it wouldn't be the first time you've seen them. And these topics are like the transfer function, for example. We need to tell you what the transfer function is. And there's another catchphrase, or is something we call the impulse response function. And I'll tell you a little bit about that. All right, but the focus, of course, is on what we're supposed to, on covering what we're supposed to cover in this course, which is simply how to find convolution of two things, what is a convolution, and how do you take a Laplace of a convolution, which is what the convolution theorem tells you. All right, so let's start with the definition. So we need to know what is a convolution of two functions. So definition. So definition, convolution integral. And this is going to look scary when we write it down, but again, like everything, when we start doing examples, it will make a lot more sense to you. Okay, so the assumption first is that suppose that you have f and g are piecewise continuous functions on the interval 0 to infinity. Okay, and so that's important. Why do we need that? Because that guarantees that we can take a Laplace transform of them. So that's a prerequisite. Then the special product. So immediately we realize that what we're going to call a convolution is some kind of special product. The special product defined by f, then an asterisk symbol g. Or this should be denoted by, actually. I'm going to put denoted by. So that's the notation for it. Denoted by that symbol is defined by the integral and here comes the integral. So f asterisk g equals an integral from 0 to t of f of tau. Now be careful, that's not a t, that's a tau, it's a Greek letter, times g of t minus tau integrated with respect to tau. Okay, I don't want you to get confused with the tau. I don't want you to get thrown off too much with the tau. Tau is just another letter other than t. So they didn't want to use t, they used a Greek letter to be fancy, so they used tau. In fact, you could actually write the same definition and replace tau with something else. Like in some, I think your book actually uses w. So they use f of w, g of t minus w dw. So either way, they both mean exactly the same thing. Okay, so let me go ahead and delete that. So again, tau is just another letter other than t. It's another variable. Okay, so that's it. So that's what the convolution is. So for starters, please do not think that this is multiplication. This is not a Laplace transform, right? Even though it starts with 0, it's not a Laplace transform, because remember, Laplace transform is a function f of t times e to the negative st dt, and you're going from 0 to infinity. So this is completely different. So this is just a definition of what it means to apply the convolution of two functions. Somebody defined it this way. Now, for our purposes, we don't worry too much about why. We just need to know how to compute this if somebody asks me to find the convolution of two functions. And also, what would be useful about this when it comes to solving differential equations and how it relates to, for example, a circuit analysis. Okay. And what's the Laplace of this? Like, how would you take a Laplace transform of a convolution? Okay, so these are some of the things we're concerned with. So first, let's get started by, so let me box this up here. So this is the important definition of what a convolution is. So this is our first milestone. Okay, now, let's find the convolution of two functions, right? So let's pick two functions. And to keep it simple, we'll start with two simple functions. What if I'm going to take a convolution of, say, 1 with sine t. Okay, so this will be an integral from 0 to t. And already I have a decision to make. So if I'm going to use this formula, I need to decide which my function I'm going to treat as my f of t and which function I treat as my g of t, or g of t. So one of these is going to be f of t, one of these is going to be g of t, right? And that's important because in my convolution, the f will get the tau and the g will get the t minus tau. So it will get the time shift basically by tau units. So here is a good piece of advice that will help you here. It's always a good idea to plug the t minus tau in the simpler formula out of the two. That's going to make your life easier when it comes to computing the integral. So one formula is one formula is just sine t. Which one would be easier when you plug the t minus tau into it to get a simpler formula? Well, I definitely don't want to put the t minus tau into the sine, because then I have a sign of a difference to contend with. So I'm going to plug that into the function 1, which, by the way, 1 is a constant, so that's not going to change. Right? And the tau will go into the sine. So that's what I'm going to treat as my f of t. So that's the first decision you have to make. So I'm going to treat this as my f of t, and I'm going to treat this as my g of t. So let's actually write those on the side. So g of t is 1, and f of t, I'll just use a different color here. F of t is sine t. But remember, what's supposed to go inside the integral are f of tau and g of t minus tau. So good news. G of t minus tau, it's still going to be 1, because 1 is just a constant. So that's good news. So you see, that makes my life easier. Inside the integral, I'm going to get simpler function in there. And f of tau, it becomes sine tau. Okay, so those are the pieces that will go inside my integral, and they get multiplied together. So this becomes 1 times sine tau, and of course I have to integrate with respect to tau. So the good news, that's basically just the antiderivative of sine. So this becomes negative cosine tau evaluated between 0 and t. So if you put t into this, you get negative cosine tau. Tau becomes t, so you get negative cosine t, minus, now put the 0 in there. What's cosine of 0? Cosine of 0 is 1, so it'd be minus minus 1, so it becomes plus 1. So the convolution of those two functions is the function 1 minus cosine t. And that's it. That's the answer. We just computed our first example of a convolution. Okay, so what do you notice? Well, immediately I notice that when I convolute two functions of time, I get a function of time, right? So when I take f of t convoluted with g of t, I expect a function of t to come out, right? Now that's really not surprising when you look at the integral, because the integral is going to be in terms of tau, but then you're going to plug in t into the tau, and you plug in 0 into the tau, so you expect the result to be a function of tau, a function of t. So that makes sense. Now the part that's ugly about this, as you'll see, is if one of the functions is not a constant, then you're going to get much more complicated integration problems, right? So things get a little bit uglier inside. So let's try our hand at another one, and we'll try one that's a little bit harder, that way so you see that we're not just doing the simple examples. And we will also see if there's anything from our knowledge from trig or other areas that could help us, like Calc 2 or integration techniques, that could help us when it comes to doing these. All right, so let me go ahead and pick out an example. So how about if we take, what if we take e to the t. So let's do e to the t and convolute it with sine t. So what if I ask you to take e to the t and find the convolution of that with sine t? So again, this is a good opportunity for you guys to practice this. So try it by yourself and then come back and see what I come up with. So first thing I need to do is obviously set up my integral. So it's going to be 0 to t d tau. And I have to make a decision. Should I put the t minus tau part in this function, or should I put it in this function? And this now becomes a little bit trickier because it's not as obvious which one would be simpler, right? So this is actually one of those examples where you could go either way. It's going to be just about the same amount of work. So I'm going to make a decision. Let's go ahead and treat this as my f. So this right here is f of t, and treat this as my g of t. Now remember the formula? The formula, I'll write it just so we have it in front of us. This, what's inside should be f of tau times g of t minus tau. So I need those two pieces. I need the pieces in red here out of the pieces in green. So let's do that part on the side. So I already know f of t is e to the t, but I need to graduate that to f of tau. So what's f of tau? Well, you just replace t with tau, so it becomes e to the tau. Good, so we at least got that part figured out. How about g of t? G of t is sine t, but we want g of t minus tau. So the simple operation means take t and replace it with t minus tau. Everywhere you see t, well, this becomes then sine of the quantity t minus tau. So these two are the pieces that I'm going to multiply and have inside my integral. That's how you construct this. So this is going to be integral from 0 to t of e to the tau sine t minus tau d tau. Okay, so now challenge time. Now this is where you have to crack this integral, right? So you have to figure out how do you do this integration. And keep in mind that tau is your variable. So how do you do this integral? Right, now this is where calculus is going to come in handy. So I will well, I mean, you could do this several ways, but one thing you could do is you could first break this open here, the sign of the difference, or you can just jump straight to integration by parts. But I'm not going to go through the technique to save us time because I have some other things I want to make sure I focus on. But this is one of those integration by parts that's circular. This is one of those integration by parts that goes around in circles. So you do it once, you get something different, and then you have to do integration by parts again, and you come back to this one. And then you set them equal, and then you solve for this integral, and that's how you get the answer. So if you do all that, and again, I'll leave that as an exercise, this problem ends up giving you 1/2 times negative sine t minus cosine t plus e to the t. So again, that would be a challenging exercise for you to review something you learned in calculus there. But that's how you would do this integral. But even though you may know how to do this, it's not fun. It's one of those really ugly integrals. So that shows you that when you're doing convolutions in general, it's not always an easy thing. So actually, in a daily life, in real life, when engineers work with convolutions, they often leave it as an integral like this. And when they leave it as an integral, it allows them to approximate it using numerical integration techniques. And they can do it for bursts of time. So they want to know maybe what would be the convolution over the first 10 seconds. So they do the integral from 0 to 10, and they punch this in a computer solver, and they let it run and get an approximation. So they get a decent approximation that they can work with. So in real life, engineers hardly ever have to do these kind of integrals by hand. It doesn't matter how ugly the integrals become. They use numerical integration techniques. Okay, so that's really what a convolution is, right? Now, is there some qualitative sense of what a convolution is? It turns out convolution has a much broader interpretation than this just take two functions and do this to them. Because this integral here is an accumulation of a certain sum. Remember, integration is typically a sum. Sum of what? It's sum of some kind of function multiplied by another function. Now, typically, when you do this, typically the first function will represent some kind of rate of change, right? And the other function will be kind of related to that rate of change. So the convolution gives you some kind of interpretation of what the total amount is of some substance that you accumulated. So for example, that substance you're measuring could be money, could be radioactive material, could be heat, could be energy, could be concentration, could be anything. The convolution basically will measure what's the total amount of that substance that you're trying to analyzing, and at time t. And you can think of the substance as added at a rate f of t, and g of t is the amount that the substance changes or grows or decays. So for example, this could be some kind of chemical reaction or some kind of radioactive decay going on. So f of t will be the rate at which the h of t will be the amount at which the substance is decaying. And if you're adding more of that substance, f of t would be how much are you adding to the reaction, right? So this the convolution can measure, can give you some kind of metric on what's that accumulation or what's that total substance you have in the system at any time. And that substance could be energy, could be again heat, could be many different quantities and applications, right? So that's, by the way, a broader sense of what this integral is. I don't want you to get stuck too much and just know you've seen a convolution, you've seen how to compute it mathematically, but without really having a good qualitative sense of what convolution really means, right? So that's one area where convolution is used. All right, now, how about the convolution theorem? So the convolution theorem. Again, assuming that f and g are both functions that are piecewise continuous from 0 to infinity, and they have to be of exponential order. So f and g are piecewise continuous on 0 to infinity and are of exponential order, and they don't have to have the same exponential order, so they just have to be bounded by some kind of exponential, each one of them. So what does that, by the way, guarantee? That guarantees that you can take a Laplace of them. So here's what the convolution theorem says. It says that if you take a Laplace of f convoluted with g, the answer is simply going to be the Laplace of each multiplied together. So you just take the Laplace of f of t and multiply it by the Laplace of g of t. And so that means it's capital F of s times capital G of s. Now this seems like a benign result, but it's a very powerful theorem, as you'll see. So we're going to show you several aspects of this theorem that make it very powerful and useful. The first one is obviously interesting because if you're trying to take the Laplace of a convolution, this theorem bypasses doing the integral. So computationally, this is a lifesaver, because if you're trying to see what the convolution is doing in the S domain, in the frequency domain, then what this is saying is don't go ahead and do the convolution, find this ugly integral, and then take the Laplace of it. No, the answer is simply going to be take the Laplace of each function and then multiply the answers. So let me actually show you both sides of that coin to see how that would work out. So let me pick another example, and we're going to actually first compute a convolution. Again, just one more example with convolution. So let's say I give you, let's see, what example should I use? Well, we'll do t convoluted with cosine. Okay, so let's do it the long way, right? So let's just compute what the convolution is. It'll be the integral from 0 to t. And I'm going to put the t minus tau in this because it'll be easier. And multiply it by cosine and put the tau here, d tau. All right, so what's nice about this is I can do it again by integration by parts. So I'm gonna so I've got an algebraic, this is like an algebraic function here. And this here is a trig function. Again, if you use this mnemonic, L-I-A-T-E. L is for logarithmic, this is for inverse trig, this is for algebraic, this is for trig, this is for exponential. Then we know that if you have an algebraic function, check, and a trig function, check. The one that's higher on that list is the one you should let u equal. So I'm going to let u equal to t minus tau. So du will be -1 d tau, because remember we're deriving with respect to tau, not t. T is treated like it's a constant. And then dv is going to be cosine tau. So the antiderivative of that, which will be, so it will be d tau. The antiderivative of that, v, would be sine tau. According to the integration by parts rule, this is going to equal to u times v. So the product of these two, t minus tau by sine tau, evaluated between 0 and t, minus the product of these two integrated between 0 and t. So minus minus becomes a plus, integral from 0 to t of sine tau d tau. All right, this part becomes, if you put the t in, it's 0. If you put the 0 in, it's 0 also. So this is actually gone, which is good, right? Because if you replace tau with t, you get 0. If you replace tau with 0, you're going to get 0. So, and this part is going to be negative cosine tau evaluated between 0 and t. So this becomes negative cosine t plus 1. Okay, good. So we know that this is the convolution of those two functions, right? So this is the convolution of those two functions. So I'm going to do the Laplace of this convolution using this answer, and I'm going to do the Laplace of this convolution using the convolution theorem and show you that you get the same thing. All right, so let's do the Laplace of t convoluted with cosine t. So that means it's going to be Laplace of this integral, which is equal to this. So if I just use the result, this is the Laplace of 1 minus cosine t, which would be Laplace of 1 minus the Laplace of cosine t because of the linearity of the transform. So this gives you 1 over s minus s over s squared plus 1. We're not going to leave it like that. Let's make it into a single fraction. So I'm going to multiply by s over s, multiply by s squared plus 1 top and bottom here. So this becomes s times s squared plus 1. And up top I'll get s squared plus 1 minus s squared. So these cancel. And this gives you 1 over s times s squared plus 1. So if the convolution theorem did not exist, the only way I could have done this Laplace of this convolution is exactly this way. And notice it's basically filled up half a page. And this was mild because, again, I picked an algebraic and a trig function. It wasn't too bad. But if I wanted to do the Laplace from the start, I can use the convolution theorem, and I wouldn't have to go through computing the convolution integral first. So second method, using the convolution integral, the convolution theorem. Convolution theorem says, you know what? Don't worry about computing the convolution. Just take the Laplace of t and times the answer by the Laplace of cosine t. So that would be 1 over s squared Alright, let me double check here. Yeah, 1 over s squared multiplied by s over s squared plus 1. So there's something nice that happens here. One of the s on top cancels with 1 in the denominator, and you're going to end up with 1 over s times s squared plus 1. And lo and behold, it's exactly the same answer. Okay. But look at that. That shouldn't even take me 3 lines, really. That's because I was running out of room. Could be done in 1 line. And look at this. This took so much longer. So that's one area where convolution theorem is a lifesaver already, computationally. That's one powerful aspect of this. But again, that's not the only aspect. So there's another interesting aspect of this. All right. To understand this, I'm going to take you back to the typical second order differential equation with constant coefficients. So let's go ahead and write a typical second order differential equation with constant coefficients and show you how this will work out. So if, let's say, I have a y double prime plus b y prime plus c y equals some function f of t, and we're going to call this 0. This is called the zero state system, which means the initial conditions are all zeros. So we're going to make y of 0 equals y prime of 0 equals 0. So the initial conditions are 0 across the board. So let's see if we can at least use the Laplace transform and see what's the pattern of the kind of solution, or what are we going to run into when we're trying to solve this, right? So if you do the Laplace transform, this is going to be A times Laplace transform of y double prime plus B times Laplace transform of y prime plus C times Laplace transform of y equals Laplace transform of f of t. Okay, now let me remind you that the Laplace transform of y prime is s times the Laplace transform of y, so y of s minus little y of 0. The Laplace transform of y double prime is going to be s squared y of s minus s y of 0 minus y prime of 0. But keep in mind, we just said that the y of 0 and y prime of 0 are 0, so this is going to be gone. So this part right here is only going to give you this term here. And this part right here is only going to give you this term here. So this becomes a s squared capital Y of s plus b s times capital Y of s plus c times capital Y of s equals Laplace of f of t, which we could, by the way, write as capital F of s. Okay, again, remember the pattern. When we do this, we factor out the y of s. So this becomes as squared plus bs plus c equals f of s. So y of s is equal to 1 over as squared plus bs plus c multiplied by f of s. Okay, now this is an interesting outcome here. So let me box this. This is really crucial result. Keep in mind, I'm working in general here. I kept the coefficients generic and I kept the right-hand side generic. Could be any function. So I'm getting an interesting pattern here. Look what the pattern is. Basically, the Laplace transform of my solution, that's what y of s is. Y of s corresponds to my solution in the s domain, in my frequency domain. And remember, we typically, as mathematicians at least, because engineers don't even have to go back, we like to go back to little y of t because we want to get the solution of little y of t to this differential equation. So we like the solution in the time domain. But engineers actually like to stop here because based on this, and specifically this part right here, they can know exactly what's going on with the system. They can understand and analyze the system and the behavior of the system through this part right here. They don't even have to go back to the time domain. So this part right here is typically designated by capital H of S, and it has a special name. We call it the transfer function of the system. And this is used a lot in circuit analysis because a lot of circuits, especially RLC circuits, can be modeled using an equation like this. So anytime you're dealing with a RLC circuit, you basically you're going to end up at the same spot. You're going to end up with something that fits this pattern. And understanding what's going on in the circuit is going to boil down to really understanding the H of S, the transfer function. The transfer function is going to tell all. All right, one more thing to mention about the transfer function. Again, something that's not our purview. We didn't spend time talking about it. It turns out that this right here, this H of S, is the Laplace transform of a special little function. Let's call it H of t. So how do you find that, by the way? Well, you could, if the bottom factors, you could factor it and do partial fraction decomposition, and you can retrieve H of t. You can recover H of t that way. Or if it doesn't factor, you'd use that trick that we showed you in previous videos. You do complete in the square and then do the inverse of the first translation theorem. So either way, we know how to crack open something like this, right? All right, so what's significant about this, it turns out that this special little function here also has a special name. We call it the impulse response function. Okay, what does that even mean? Well, that's basically the solution to this differential equation if you replace f of t with a special weird function that kind of models like a burst of energy, like a spike of energy that you apply to the system. It's like a way of jarring the system instead of applying, you know, like even a unit step function, that's kind of too long. So an impulse should be even shorter than, so it should be like a step function but applied over a short burst, really short burst. And we have a special name for that function. It's called the Dirac function. And it's symbolized by delta of t. And it turns out that if you take this differential equation and put in lieu of f of t, put delta, so put the impulse function, the Dirac function on the right side, the solution will be y of t equals h of t. So the solution to this is kind of interesting, because if you try to solve, right? So if you try to solve, so if you invert all of this, what are you saying? Well, you're saying that little y of t is going to be the h of t times the inverse of this. That will be the convolution of f of t. Okay, see what I did there? I used the convolution theorem. Because if you invert this product, right? If you invert this product, the convolution theorem that says that if these are multiplied in the S domain, their inverse is going to be the convolution in the time domain. Okay. Here's the convolution theorem. Write the inverse of that. If you take the inverse of this, you're going to go back to this. So the inverse of f of s times g of s is going to equal the convolution. So a nice way to kind of think of this, and this is how engineers like to think of it, is product in the frequency domain means convolution in the time domain. So again, arithmetic product in the frequency domain means convolution in the time domain. Okay, hold that thought. So going back to this part, if I already know that y of s is the product of these two, then the inverse of this is going to be the convolution of the inverses of these two. So that's what we're writing here. And again, remember what I'm saying here. This is true in general. I didn't pick specific numbers here. I didn't pick specific function. So this is a generic way of understanding the behavior of the circuit that this equation represents. So again, in real life, engineers use this to their advantage, because the way they look at it is, if I want to get a solution for any given driving force, it basically boils down to taking the solution h of t, which is the impulse response function. So it's the solution from applying this special function, and then convolute that with the driving force, and it will give you the new solution. So every solution relates to the solution from the impulse function, Dirac function, as your driving force, which is a very powerful result, because once you understand that, then you basically model every response. All you do is just change the f of t. So if you change the right hand side here, you just change f of t and do the convolution, and you'll get the new answer. You don't have to go through all this stuff anymore. Right? So this is a very powerful part. And again, The h of t is called the impulse response. The Laplace of it, the capital H of s, is called the transfer function. Now again, engineers typically don't do what we like to do, so they wouldn't go back here. They would actually stop at the h of s, and based on that, they can already get all the answers they want about the system. They typically understand everything going on with the circuits by just studying h of s. So they do all their analysis in the frequency domain, and they don't need to go back to the time domain to understand what's going on. All right, so this is, again, beyond our requirement for our course, but this is something that you might find helpful when you take circuit analysis, or if you have to take circuit analysis or control theory, you will come across these topics again. Okay, for our purposes, as far as our course and our exam, you really just need to know how to do a convolution, and you need to know how to do the convolution theorem. So how do you do a Laplace of a convolution? So by doing just the Laplace of each and multiplying. All right, so those are the important topics for you to keep in mind. Okay, so this concludes the series on Laplace transforms. I hope you found it helpful. And again, as usual, please do not hesitate to let me know if you have any questions. And thank you for your time.